Hi, in this video we will be revisiting the concepts of Riemann sums and definite integrals, which you probably encountered in a previous calculus course. Let us start with the definite integral. Given a function f of a single variable x, such as the one you can see here, the integral of this function over the interval a to b has this formula. We can visualize this definite integral as the signed area between the graph of the function and the horizontal axis. If f is not too hard, we can determine its antiderivative f and use the fundamental theorem of calculus to determine the definite integral exactly. You can prove this part of the fundamental theorem of calculus by taking the limit of a so-called Riemann sum. The limit of a Riemann sum is also what was used in defining the definite integral initially. So let us revisit this definition next. Here you can see a definition of the definite integral for a function f of the variable x on the interval a to b. As you can see, the integral is the limit of a finite sum of the product of a function value and the width of an interval. Note that the function value for each interval is the function evaluated at a random location within the same interval. The part within the limit is called the Riemann sum. Let us return to a visualization to explain this definition. Here you can see the same function as before, including the signed area that represents the integral. First, we will add a visualization of a Riemann sum with a small number of intervals. We divide the interval a to b into 5 intervals of the same size delta x, and in each interval we select a random point. For each of these points we calculate the corresponding function value. Each product in the Riemann sum now resembles the area of the rectangle with width delta x and as height the function value for that interval. As you can see, the Riemann sum is an approximation of the definite integral. Each of the rectangles covers a region of the integral, but also misses parts, and at some points does not even overlap with the integral. The next step is to visualize taking the limit of the Riemann sum. This means that we need to increase the number of intervals, which we can do by doubling that number several times. After doubling one time, we get this image. Another doubling gives the following. Do you notice that the Riemann sum still looks like an approximation of the definite integral? Because the limit states that we must increase the number of intervals to infinity, we can keep doubling and doubling. As soon as the number of intervals is high enough, we barely see any difference between the exact integral and the Riemann sum, as we should have expected from the definition. Now we have reviewed the concept of definite integrals and Riemann sums, and we can try to put an end to this video. But wait, I can think of a lot of reasons why it might not be possible to evaluate a definite integral exactly. One of those reasons I want to share with you. What if you do not know the function on the entire interval, but only have a limited amount of function values? How can we then calculate the definite integral? Or if that is not possible, can we do an approximation? And what is the best way to do this approximation? And how good is this approximation? Well, the answer to the last questions will be a topic for another time. But for now, we'll take a break. Bye!